Hi, hello everybody. Welcome back. This is Ankita Menon, and today we are delving into the third session of surface chemistry. Topic of discussion is desorption activation energy. Desorption activation energy. Now, before that, just a quick revision of what we discussed in the previous session. We discussed what are the causes of adsorption. We said that the only cause of adsorption are the residual forces. The thermodynamics of adsorption is governed by delta G is equal to delta H minus T delta S. And we said that if the adsorption should happen spontaneously, delta G would be negative. And if it should remain negative, the modulus of the enthalpy, as it is exothermic, should be greater than the modulus of T delta S. And finally, we ended the session with the comparison of three types of adsorption isotherms. One was, or three graphical representations to be precise. The first one was isotherm, adsorption isotherm, where the temperature is kept constant. Iso means same, therm means temperature. Temperature is kept constant, and the plot is plotted between the extent of adsorption theta versus pressure. The next graph is isobar, where the pressure is kept constant and the graph is plotted between extent of adsorption versus temperature. And the third plot is an isostern, where the extent of adsorption is kept constant and the plot is between pressure versus temperature. The ideology behind these patterns of graphs were discussed in the earlier video. The links of those videos, video 1 and 2, will be attached in the description box. Okay. Now, let's begin today's session, which is actually a numerical based session today. Okay. So the topic as discussed is desorption activation energy. Okay. So we are talking about physisorption in particular. And physisorption, we know, is governed by very weak bonds. Not even bonds, van der Waals forces of attraction. Correct? So we are talking about physisorption. Again, this is a revision of what we discussed in video 1. Physisorption happens between adsorbate molecules onto the adsorbent surface through weak van der Waals forces. Van der Waals forces of attraction. So as these van der Waals forces of attractions are low in magnitude, they can be easily detached. Correct. So the amount of energy, please note it down. The amount of energy which is required to cause desorption is the definition of our topic of discussion. Is desorption activation energy. Desorption activation energy. So I think it is very clear. So here we have a solid surface onto which we have weakly bound gaseous molecules. The interaction between the gaseous adsorbate and the solid adsorbent is weak van der Waals force, and in order to remove that, we'll have to give some amount of energy. The amount of energy which is required to remove the gaseous molecule from the solid surface to cause desorption is called desorption activation energy. Okay, now let's come to the numerical part. Let's say that you have a gaseous molecule along with a solid surface, and we know that they are in equilibrium and they are reversible to form GS, correct? So forward direction, we see adsorption happening. And in the reverse direction, we see desorption happening, which is the opposite of adsorption. Correct. Now, we have already learned kinetics, correct? And again, I can attach the playlist of the kinetics in the description box. You can refer to that, wherein we learned something called the Arrhenius equation. From the Arrhenius equation, we know that K is equal to A e to the power minus EA by RT. This is something that we know. Okay, now what I'm going to do is I'm going to take the reciprocal of this Arrhenius equation. So if I take the reciprocal of the Arrhenius equation, what do I get? I get 1 by the rate constant is equal to 1 by the pre-exponential factor e to the power minus EA by RT is what I get. All right, this is what I get. Now, 1 by K in surface chemistry is notated as gamma. Okay, so 1 by K is gamma. 1 by the pre-exponential factor is gamma naught. And when this term comes to the top, it becomes e to the power plus EA by RT. I hope you get it. So K is the rate constant. You know this if you have followed the channel. A is the pre-exponential factor. Pre-exponential factor. Okay. EA is the activation energy in this case. Correct. Now, as we have taken the reciprocal, here in this term, the activation energy that you get from here, e to the power plus EA by RT, is the desorption activation energy. Desorption activation energy. Okay, so this is it. This is the equation. Gamma is equal to gamma 0 e to the power plus EA by RT. Again, this is a pre-exponential factor itself because this is the exponential term and gamma 0 is the prefix to this. So this is also a pre-exponential term, but we have to be careful with the units. That's all. We have to be careful with the unit. Always, you know that the exponential term is unitless, always. Always the exponential terms would be unitless. So the unit of gamma is going to be the unit of gamma naught as well. Gamma naught as well. Now for desorption, GS is G plus S, correct? This is what desorption is about. So assuming that it is first order, let's say that this is first order. Let's assume. So if it is first order, if it is a first order reaction, the unit of rate constant is going to be per second. Again, this all comes from chemical kinetics. I'll be attaching the playlist of the same in the description box. Please watch it out if you're not sure with this, okay? So if we have to take gamma, if we have to find the unit of gamma, what is gamma? Gamma is 1 by K. So of course, unit of gamma is going to be 1 by per second, or the reciprocal of this, which is just second. And we already know that the unit of gamma is equal to the unit of gamma naught. So the unit of gamma naught is also seconds. Seconds, just time. So the physical meaning of this is, as your desorption activation energy increases, as the desorption activation energy increases, it means it is difficult to desorb the gas from the solid surface. Correct? Then the value of gamma will also be high. The value of gamma will also be high. Why? Because if EA is high, this is EA, correct? This is EA. If the desorption activation energy is high, e to the power EA by RT will also be high. And we know that this is directly proportional to gamma. That is also going to be high. Okay. If your value of gamma is very high, it notates the lifetime of adsorbate on the surface is high. on the surface is high. I hope you get it. Lifetime of the adsorbate means the time for which the gaseous molecules reside on the surface. Okay. For example, you have two solid surface. Here the gamma value is, let's say, x units, and here let's say your gamma value is 10x units. So if gamma is 10 times higher than x, it means that the lifetime of the gaseous molecule on this particular surface, let's say this is surface 2 and this is surface 1. So the lifetime of the gaseous molecule on surface 2 is higher than that of 1 because the value of gamma is high. So the lifetime would be high, and also the activation energy which is required to desorb the gaseous molecule from the surface will also be high. Okay. So you will, or you can get questions in GATE. So in earlier times, it was only in GATE. Nowadays, they're asking for CSIR-NET exams as well. Now, the other scenario is if you have two different temperatures and they ask you to find the value, very easy. So let's say that you have two different temperatures. So gamma 1 is the lifetime at temperature T1. So it's going to be gamma naught e to the power desorption activation energy by RT1. Right. And then you have gamma 2, which is equal to gamma naught e to the power EA by RT2. We are assuming that the desorption activation energy at two temperatures do not differ. If so, this is 2, this is 1. Let's divide 2 by 1 or 1 by 2. Anything is fine. You're going to get the same answer. So what do we get? Gamma naught e to the power EA by RT2 divided by gamma naught e to the power EA by RT1. Correct? Gamma naught and gamma naught get cancelled. Here what you have is e to the power EA by RT2. This comes to the top and becomes EA by RT1. Okay, so this is going to be gamma 2 by gamma 1. Now I'm going to take natural log on both sides. So when I take natural log on both sides, natural log of gamma 2 by gamma 1 is equal to natural log of e to the power EA by RT2 minus EA by RT1. Now natural log of E is 1. So this becomes natural log of gamma 2 by gamma 1 is equal to EA can be taken outside, R can also be taken outside into 1 by T2 minus 1 by T1. Okay, so there are two important equations that we have discussed here. One is this, equation number 1. I'll change the ink. Equation number 1, important. Lifetime of a gaseous molecule on the surface is equal to the pre-exponential factor into e to the power desorption activation energy by RT. And the next one is if you have two different temperatures. This is equation number 2. And this is how the equation comes to be. We'll try to solve a question from both these equations, and then it will be easy for you. Okay, so note down the first question. Please note down the first question. So this question was asked in GATE 2008. I'll read out the question. Please pause the video, note the question, and then try it out if possible, or else we'll do it along. All right. So physisorbed particles undergo desorption at 27 degrees Celsius. So first of all, temperature is given as 27 degrees Celsius. We know that any temperature is given should be converted to the Kelvin scale, and hence this is equal to 300 Kelvin. The activation energy, so it undergoes desorption. So whatever energy is given will be associated with the desorption activation energy, and that is 16.628 kilojoules per mole. Kilojoules per mole. So if I have to convert it to joules per mole into 1000, this is 16,628 joules per mole. Okay. Assuming the first order process and the frequency factor. So we already know the unit of the pre-exponential factor if it is first order. Just let it be there. Frequency factor is 10 to the power 12. Again, frequency factor, you can understand this term only if you have learned kinetics, or you can also understand it by the units. Okay, so frequency factor actually means A. And it is also notated in hertz. Hertz means per second. Okay, so A is 10 to the power 12 hertz, which is equal to 10 to the power 12 per second. So what do we want to find? The average residence time. Average residence time means we have to find gamma of the particle on the surface. It's very easy. Everything is given. Let's try to plug. So we know that gamma is equal to gamma naught e to the power EA by RT. Right? Gamma is what you have to find in seconds. So we have to put gamma naught in seconds as well, because the unit of gamma is equal to gamma naught. Right. Now gamma naught is 1 by A. Correct. So that is 1 by 10 to the power 12 per second. When it comes to the top, it will become second. E to the power EA. Activation energy is 16,628 joules per mole divided by value of R is 8.314 joules per Kelvin per mole. And you have the temperature, which is 300 Kelvin. So now you can see joules get cancelled, per mole gets cancelled, and this per Kelvin also get cancelled. So the pre-exponential factor, sorry, not the pre-exponential factor, the exponential factor over here becomes unitless. Becomes unitless. So when you solve this, you will get it around 785.77, the exponential term, into this comes to the top and it becomes 10 to the power minus 12. Per second comes to the top, seconds. So you can see that such an option is not there. Everything is just rounded off to one integer. So I'll take it 2 points to the left. So this is 7.85 into 10 to the power minus 10 seconds, or it can be approximated as 8 into 10 to the power minus 10 seconds. So this is the average residence time of the whatever molecule that they have given on the surface. Option A. Option A. Next is a rank booster question from desorption activation energy asked in December 2024. So earlier these type of questions were only asked in GATE, but now as you have access to the calculators in CSIR exams as well, you get numericals in NET exam as well. Okay, so let's try out the question. The average time for which a hydrogen atom remains adsorbed. So the data which is given is of gamma on a surface is 35% shorter at 1000 Kelvin than at 600 Kelvin. The activation energy in kilojoules per mole for the desorption is closest to. Okay, so based on what we have already learned, let's try to solve it. We already know that gamma 1 is gamma naught a to the power, gamma naught e to the power EA by RT1. Now see, there are two temperatures given. Let's consider 600 as T1 and 1000 as T2. So we'll take this as equation number 1. And about gamma 2, gamma naught e to the power EA by RT2. This is 2. If I divide 2 divided by 1, what I get is gamma 2 by gamma 1 is equal to e to the power EART2 minus EA by RT1. And this EA is what you have to find. EA corresponds to the desorption activation energy. Desorption activation energy, right? Now, if I take ln on both sides, natural log on both sides, what I get is ln of Gamma 2 by gamma 1 is equal to EA by R into 1 by T2 minus 1 by T1. Easy. Now see what is given in the question. You have to find the desorption activation energy in kilojoules per mole. So if you have to find it in kilojoules per mole, the unit of R that you'll be putting will also be in kilojoules per mole, 8.314 into 10 to the power minus 3 kilojoules per Kelvin per mole. T2 is the temperature, 1000 Kelvin. T1 is going to be 600 Kelvin. And gamma 2 by gamma 1. See, already they have given that gamma 2, which is the residence time at 1000, is 35% shorter than that at 600. So what does it mean? It means that gamma 2 is equal to, initially it was gamma 1, and then when the temperature got increased, it reduced by 35%, right? Now, 35% in numerical value means 0.35. It is reduced, so you have to subtract 0.35 gamma 1 from gamma. That's it. So, gamma 2 is equal to, when you subtract this, you will get 0.65 gamma 1. So, you can substitute that. What do we get? We get ln of 0.65 gamma 1 divided by gamma 1 is equal to EA by 8.314 into 10 to the power minus 3 into 1 by 1000 minus 1 by 600 is what you get. Gamma 1 and gamma 1 gets cancelled. Here the temperatures are in Kelvin. So the Kelvins over here, the units, kilojoules per Kelvin per mole, right? So per Kelvin and Kelvin also gets cancelled. And at last, what you have is in kilojoules per mole. So you can rearrange this. Okay, I hope you understand how Kelvins got cancelled. I hope so. So that is, I'll show you once. Ln of 0.65 is equal to EA by 8.314 kilojoules per Kelvin per mole into 600 Kelvin minus 1000 Kelvin is 400 Kelvin. I'll write it like that. Minus 400 Kelvin divided by 1000 Kelvin into 600 Kelvin is what you have. So initially, this Kelvin and one of the Kelvin from the denominators get cancelled. And next, you have per Kelvin over here and you have a Kelvin left over here. So whatever you have remaining is just kilojoules per mole. This is what you have, right? Now you can rearrange this. EA is equal to 8.314 into 10 to the power minus 3. You take this here. Into ln of 0.65 into 1000 into 600 divided by minus 400. You can calculate this. See, ln of a value which is less than 1 is going to be negative. So this negative and the negative sign over here gets cancelled. And finally, the value of EA that you're going to get is 5.37 kilojoules per mole. In the question, they have asked us to round it off to the closest value among the options A, B, C, D. In option D, you can see 5.4. What we have got is 5.37, and hence the correct option is option D. All right. So I hope you have got an idea now. We'll see you in the next.